So here are our results. So all this was processed in MATLAB in the results that we see. The one on the far left is the noise-free and no data dropout condition. So this is the simplest tracking that we can do. The vertical axis is error rate, or error, I'm sorry, in pixels, and on the right is the frame number. So frame 1, frame 2, etc. Now the red plot that you see, that's the error when using the foreground detector. The error in pixels, how far away the predicted center of the blob was from the true center. Now the reason we have such big jumps in the red is whenever the algorithm was starting, and then whenever the blob entered the screen and left the screen, there was a little bit of error there, obviously. But it if you look at the red, it's about at 1 pixel in its error. It moves up and down, but it's about 1. Now the green was via the Kalman filter, the error that was measured from the Kalman filter. Now we can see that at around frame 10 through about 40 to 50, the error is worse, but then the algorithm is able to compensate, and we see at about frame 60 and onward that we actually have less error using the Kalman filter, using that the mathematical model, and the error gets lower. Which shows us that using the Kalman filter reduces the error in object tracking, which is great. But that was the easy case. That's no data dropout, there's no error. Let's look at the right. Now, when I said that there was no data dropout, it's a little bit of a misnomer. What I mean is that there's no intended error dropout. So if you were to watch the video for this plot, you would see the blob moving across a noisy background and not passing through the rectangle. So there's no intended data dropout. But because the noise, affected the foreground detector, we actually do have data dropout that we see. But it turns out it's not a problem. So say between frame 40 to 46, if you look at the red plot, there wasn't any data that was recorded there. But again, it's all right. Looking at these results, we see that the Kalman filter outperforms the foreground detector. And we can see that because the error is, for most samples, always below the red. There are a few when, the red spikes downwards, but for the most part, we have less error using the Kalman filter in a noisy condition than when using measurement data, which is a great thing. And even better is that we see when we have data dropout, we're still able to predict where the blob should be, and with an error of about 1 pixel. Again, we see this looking at about frames 40 to 45. So this obviously is a good thing. But let's look at the other two cases. Now the plot on the left is a noise-free condition, but with intended data dropout. And that's pretty obvious when you look at it. It's about frames 35 to 45. We see that big gap in the red. But that's where the blob passed through the white rectangle. And I mean, we see at the beginning that the error using the Kalman filter is better. About frame 5 to 35, the error is lower. And then, the error spikes up on both of them, mainly because it enters the rectangle and there's an edge condition. But about frame 85, again, the Kalman error gets lower than the measured error, which again shows that we're improving the error rate. And then finally, when we have an intended data dropout with a noisy condition, as we see on the right, we have better results, particularly at the beginning, around about frame 0 to about 70. After that, it gets a little iffy, but we're able to show that using the Kalman filter works. So this is all good news. But what if we want to track moving vehicles? Now, unfortunately, it's not as easy to do this. Ideally, we want to do the same techniques, the same analysis on moving vehicles as we did the blobs. But the problem is we don't know the true center of these vehicles. since the blobs were created by me in MATLAB, I obviously have the centers, I can compare them. But with moving vehicles, we don't have those centers, and so it's really hard to track and measure how well our filters are doing. So the next best thing we can do is to compare them visually. Now this is a little bit iffy, but later on I'm going to discuss more in depth on how we can improve tracking moving vehicles. Looking at the car here, we see two crosshairs, and that's where the two algorithms, the foreground detector and the Kalman filter, are trying to guess the center of the car. Now they're looking at the hood of the car as opposed to the whole vehicle for the center, but we can still use this information. The red crosshair measures where the foreground detector thinks the center is, and the green crosshair, what the Kalman filter detects as the center. And as you look at them, they're about the same. They're almost on top of each other. So we see that the Kalman filter is working about as well as the foreground detector. so that's the work I did, but I wanted to go a little bit deeper and discuss what other people do. And one individual in particular, Nicholas Obolensky, he did his master's thesis at the University of Florida, and he discussed methods of how to track moving vehicles with a Kalman filter. Now, the typical model that would be used is a constant acceleration model, and let me take a second to explain that. With the mathematical model that we use, we can choose a variety of models. We can use, say, a constant acceleration model, and that's where we know that our object has obviously a constant velocity. We can use a constant acceleration model, which says that they're always going to be accelerating at a constant value. The constant acceleration model is better than the constant velocity model because it approximates nature better, because things typically have some acceleration, so it approximates nature better. But there's a few problems with that. One big one being that if I have a constant acceleration model, say measuring a ball, say that the ball is being dropped and I'm measuring it, well, that has a constant acceleration of 9.81 meters per second squared. That's the gravitational constant. But one issue that we have is that if we were to predict the velocity of the object, that predicted velocity will eventually become infinite, which is obviously a problem because objects can't have an infinite velocity, and it's again not quite what nature is. Nature doesn't operate at a constant acceleration. The acceleration varies for a multitude of reasons, and that's what Obolensky decided to do. Instead of doing a simple constant acceleration model with this Kalman filter, he went beyond that, and he said, all right, what if acceleration is now a time-varying parameter? Now, he goes into a lot more detail into his paper, which I'm going to cite at the end of this video, but it has some interesting implications about using his method. So these are just a few of the results that he had, and he was trying to track a car from a surveillance video, and the plot on the left is the error when measuring the x coordinate, the x position, and then on the right is the y position. Now, the solid dashed line that you see is going to be whenever he used the constant acceleration model. Then the dashed line is the time varying acceleration model. If you look at both plots, the standard deviation of the error for the time varying is almost always, if not always, below that of the constant acceleration model. And again, looking at the y coordinate one, again, time varying acceleration model operates better than the constant acceleration. This is not really surprising because it's more information that we're given. And think back to the beginning. We know that we can use foreground detection to get positioning of an object. We know the mathematical model that we can use. And each model that I've been discussing has more complexity, is closer to nature. A constant acceleration model better models nature than a constant velocity one, but a time varying acceleration model models nature even better than just a constant acceleration model. And so with as the algorithms become more complex and more closely approximate nature, the error that we receive should decrease, which is easily seen by his results. So that was my project. What I did to look at how to use a Kalman filter to track vehicles, and a little bit of what other people are doing to track videos. What you see here are some references that I used, and I like them because a lot of them uh, don't go into a lot of technical detail about how to use the Kalman filter, but give a good Reader's Digest of how it's used. For instance, the one that says Kalman filters for undergrads is a great resource for those interested in learning the Kalman filter, but want to learn it at maybe a slower pace that makes more sense. That's kind of geared towards people who aren't familiar with it. Anyway, I hope you like this presentation. If you look down in the description, you should see a link to this PowerPoint and a link to Nick Obolensky's master's thesis, which I encourage you to read if you're interested. Also, I'm adding an additional link in the description that shows me walk through the MATLAB program that I've made so that you can see how the Kalman filter tracks a moving blob. Thank you.